Hello, good evening. This is Mr. Batron, and today's lesson, the complex number system. What is a complex number? A complex number is a set of numbers written in the form of a plus bi, where a and b are real numbers, and I equals the square root of -1. Now, again, this is written in the form of a plus bi, where a is your real part and b is the imaginary part. Okay? What that means is if b equals 0, we call the complex number, the whole thing, we call it wholly real. And that's only because 0 times I is going to give you 0, so you're just left with the real part. Conversely, if A equals 0, then we call this complex number wholly imaginary. That's because when A is 0, we're just left with BI here. When we write a complex number or imaginary numbers, we want to write it in the form of a plus bi. So here's an example, a couple examples. Name the real and the imaginary part of the following complex numbers. For the first one, we have 4 plus 2i. So you can put a box around the 4 in red, and in green, we're going to put a box around the 2i. All right, so if we want to name this, that means A equals 4, and our BI, or our imaginary part, is 2i. Same thing here. We have -23, and then we have -6i. So again, if we want to name this, A equals -23, which is our real part, and our imaginary part, BI, is -6i. Right. Even with fractions, you still want to put a box around the -2/7, and then we're going to put a green box over the +4/5. So that way we're naming this A equals -2/7, and BI equals 4/5i. And last but not least, you have 2 minus 4i/3. To begin this one, let's break it up. We're going to break it into 2/3 minus 4/3i. Now we're ready to name the real part and name the imaginary part. So the real part is A, which equals 2/3, and the imaginary part is BI, which equals -4/3i. Okay. Make sure that when you're writing this, remember, complex numbers are written in the form of A, your real part, plus or minus BI, your imaginary part. All right, so within the complex number system, we also have a complex axis, or the complex plane. Okay, in your real number system, on the left-hand side over here, we talked about the x and y axis here for you. And within the x and y axis, when you start at the origin, if you go left or right on the x, you have the set of real numbers. So you have the negative numbers on the left, and you have the positive numbers on the right. And if we're going up or down, you have the negative numbers as you go down and the positive numbers as you go up, with the x and y axis on the coordinate plane. Now, as we're crossing over into the complex plane, the complex plane doesn't really have an x or y axis. It has the real versus imaginary axis. Okay, so on your real axis, you have your real numbers. So again, you have your negatives going to your left, and your positives going to the right. But on the imaginary axis, when you go up on the imaginary axis, that's positive I, and when you go down on the imaginary axis, that's negative I. The real axis, again, is A, and the imaginary axis is your BI, which has your complex number. Okay. All right. Let's move on. Also, we have what is called the imaginary circle. And this can be written two ways, so I wrote it both ways for you. You have the imaginary circle right here on the left side, and then you have, basically, we're going to transfer what we know in the imaginary circle on the left side, and we're going to transfer it over here to the right side of this diagram here. So, when you start off at 0 degrees, okay, when you start off at 0 degrees, you go straight over here. That's just a line at 0 degrees. All right, it doesn't form an angle. So we say that I to the power of 0 is 1. And this may seem a little trivial. However, when you remember raising numbers to an exponent, when anything that you raise to the power of 0, that's always going to be 1. It doesn't matter if it's 2 to the power of 0, well, that's 1. You have 4 to the power of 0, that's 1. X to the power of 0, that's 1. Anything that we raise to the power of 0, x plus 1 to the power of 0, that's going to be 1 also. It's always going to give you 1. Okay? Now, we'll remember from rotations that when we rotate 90 degrees, and because 90 is positive, we go in a counterclockwise direction. So we're going to go from I to the power of 0, or 1, into the counterclockwise direction. So now our next stop is I. And that's also our first stop, so that's I to the power of 1. I to the power of 1 is I. Okay? We're going to take another 90-degree rotation. And our next stop is -1. So that's our second stop there. So that's I squared. I to the power of 2. All right, let's make another stop. Let's get around this circle here. From -1, we're going to -I. So that's your third stop. And that's I to the power of 3. All right, and let's complete the circle. Go around here. Well, this is our last stop, and this is our fourth stop, which also happens to be our first stop, which is I to the power of 4. So this is what we call a cyclic or a roundabout rotation, a circular rotation that just repeats itself. There are only 4 unique values that we get when we talk about the i's. All right? When we have I to the power of 0, that's 1. When we go around from I to the power of 0, we have I to the power of 1, that's I. I squared, or I to the power of 2, that's -1. I to the power of 3 is -I. And then we get back to I to the power of 4, which is where we started, and that's still 1 again. Okay? All right. I also created this table here, or this chart here for you. That way, if the circle is confusing, if you remember this pattern, this works out as well. The key thing to remember in red is that the definition of imaginary unit is when I equals the square root of -1. This is the second time that you're seeing this, so it's very important that it stands out to you. Okay? So again, I to the power of 0 is 1. All right? I to the power of 1 is I. I squared is -1. Well, how did that be? Well, first and foremost, I itself is the square root of -1. But if we take that and square it, when you square something that's being square rooted, it just gives you the answer that's under the square root symbol, which is -1. Okay? Here, we have I to the power of 3. That equals -I. Okay? I to the power of 3 can be written using your law of exponents as I squared times I. And by breaking it down, we know that I squared is -1. So you're multiplying -1 times I, which is just -I. It's the same thing. That's why that works. Okay. Here are a couple examples down here. We talk about I to the power 6. Okay. You can feel free to use this circle and go around it until you get to the I to the power 6. So I would start here, I to the power 0 first. So if I go here, let's go around. So let's get a highlighter. All right. So we have I to the power 0. Let's go I to the power 1. That's I. I to the power of 2. That's -1. I to the power 3 is -I. I to the power 4 is 1. I to the power 5 is I. I to the power 6 is -1. So we expect that I to the power of 6 to be -1. We can do the same thing again with I to the power 13. Okay, we start at 0 again and work our way around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I to the power 13 is I. Now we have I to the power of 95. Okay? If you think that I'm going to go around this circle 95 times, it's not possible. I'm not going to do that. All right? So it has to be an easier way. If you remember from earlier, we said that there are 4 unique patterns, or 4 unique values, that are circled throughout this pattern. So if there are 4 unique values that are circled throughout the pattern, well, let's take 95 and divide by 4 and see how many times can 4 go into 95 evenly. So I'm going to take 95 and I'm going to divide that by 4. It seems that 4 goes into 9 2 times, because 4 times 2 is 8. 9 minus 8 is 1. 4 goes into 15 3 times. All right, because 4 times 3 is 12, and 15 minus 12 is 3. So I have 3/4 left over. All right, this is very important. Not the whole number, but the remainder is going to help us. Okay? So if we go around this circle 23 times, when we start over fresh at 92, we're going to go to 93, 94, and then 95. Well, that just happens to be I to the power of 3. And according to our earlier suspicions, I to the power of 3 is -I. Therefore, I to the power of 95 is -I also. All right. If that went too fast, we can continue to work with this on our earlier examples. For instance, I to the power of 6, if I take 6 and divide that by 4, I know 4 goes into 6 one time, and I'm left with 2 as your remainder. So we're going to now look at I to the power of 2. And we said earlier that I to the power of 2 is -1. So it works out. Same thing here, I to the power of 13. Well, we're going to take 13 and divide that by 4. And we said that 4 goes into 13 3 times. Okay, because 4 times 3 is 12, and we have 1 left over. We're going to take that 1, and that's going to be I to the power of 1. And I to the power of 1, as we said earlier, is just I. So it checks out. The only way you're going to get this is if you practice. Practice makes perfect. And I promise you, tons and tons of practice with this, you're going to get much better. Let's go and see what we have for practice. All right. Well, we have independent practice here, odd numbers, to which we worked on during class. Okay. we're going to use the strategies and the skills that we worked on during class, as well as some strategies from Math 1 to help us out with being successful with this topic. So let's start on number 1. Okay, that says I to the power 30. So what do you think we should do? Are you going to go around your imaginary circle 30 times to find a value? Or you think there must be an easier way? Now, if you think there has to be an easier way, then you're right. So let's use it. Let's take this 30 and divide by 4. How many times can 30 go into 4 evenly? Okay, well, there's 7, because 7 times 4 is 28, and I have how much left over? 2. Okay, that 2 is going to come in handy because that's what we need for our I. So we have I to the power of 2. Well, what's I to the power of 2? Now, if you don't remember that, if you at least remember that I equals the square root of -1, you can help use that to your advantage because now you have the square root of -1 squared. Okay? And if you need to square it, go ahead and square it. That way it works out for you. Okay? So anything being square rooted, if you're squaring something that's already being square rooted, you just get the answer that's under it. So our answer is -1. Okay? We're going to skip down to number 3. Number 3 has 3 times I to the power of 7. Well, we're really concerned about the I to the power of 7 and not really the 3. So let's go ahead and work with that and then bring the 3 in later. All right, so I to the power of 7. All right, that's more than 4, so we need to know what's our remainder. So if you take 7 and divide it by 4, you have 4 can go into 7 one whole time, and you have a remainder of 3. Well, what's I to the power of 3? Okay. You know that I squared from just doing it times I is going to give you I to the power of 3. Well, the value of I squared from just doing it was -1. So what's -1 times I? That's -I. So I to the power of 7 is equal to -I. Let's substitute now that we have that. So you have 3 times -I, which equals -3I. Okay. Number 5, okay, you can't add terms that are unlike. As we can see, you have an I here, but you have I to the 3rd power there. You can't add those together. So we have to find out a way of, I guess, simplifying them before we operate with them. So we know I is just going to be I. But we just talked about I to the power of 3. And according to our information before this sheet, or before this page, we said I to the power of 3 was equal to -I. So what's I minus I? 0. Therefore, I plus I cubed is 0. Okay? Question number 7. Question number 7, you have 3I to the power of 4 plus 5I to the power of 6. Again, you can't just add those. You have to make sure that they have like terms in order to just add them together. So let's try to clean up these i's here. Let's work with the 3I to the power of 4. Okay? We know that I to the power of 4 is the same thing as I to the power of 0. Or if you took 4 and divided by 4, you just get 1 with no remainder. No remainder. So I to the power of 0 is just 1. Okay? Plus 5I to the power of 6. We just did that a problem ago, but just for memory, let's go ahead and take 6 and divide it by 4. And that gives us 1 whole time, but we have 2 left over. Okay? So we need to figure out, instead of I to the power of 6, we need to find out what I squared is. And we said that earlier to be -1. So let's go ahead and substitute. We're going to substitute 3 times what we said to be I to the power 4 is 1, plus 5 times negative 1. 3 times 1 is 3. 5 times negative 1 is negative 5. 3 minus 5 is negative 2. Okay. Working on number 9. Number 9, you could do one of two ways. I would urge you to pull out your good friend, the law of exponents here, because we're multiplying two exponents with the same base. So when you're multiplying two exponents with the same base, the law of exponents says to keep the base and add the exponent. So 102 minus 98, or plus negative 98, same thing. By doing that, it helps you simplify your issues here, because you know 102 minus 98 is going to be 4. So we're left with I to the power of 4. And I to the power of 4 is 1. Okay. We did do the warm-up, we did do the even problems for warm-up, and I urge you to go back through those and work through those as well, just to make sure you're practicing. Okay, but we're going to go ahead and move on. As we further through the complex number system, we also need to talk about day 2, simplifying complex expressions. Okay, back then in Math 1, you were looking at radicals such as negative 16, the square root of 16 and the square root of 48. And also you may have added or simplified radicals such as the square root of 75 plus the square root of 27. So those rules still apply. And that's fair game to what you're about to learn, or about to extend them to, really. Okay? We know that in order to simplify a radical, first, you want to list all of your perfect squares. So 1 times 1 is 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10. But you don't stop at 10, because now we're in high school. We're in Math 2. So let's go 11 times 11, 12 times 12, 13 times 13, 14 times 14, 15 times 15. You can even go to 16 times 16, which is 256. Okay, and you can continue. I do urge you to go down all the way down to 625. Okay, that's 25 times 25. Okay, so we're trying to find out the square root of 16. Well, first and foremost, you know that the square root of 16 is 4, because that's a perfect square. So we lucked out with that. But if you have something that really isn't a perfect square, look at your list of perfect squares that we just wrote and find the largest perfect square that can go into that number evenly. Okay, we want to find the largest perfect square that would go into that number evenly. That way we have less problems reducing or trying to reduce. Okay? So let's experiment with our next number, the square root of 48. Well, if I break down the square root of 48, all right, let's use the largest perfect square that goes into 48. That means we have 16 and 3. So we need to take the square root of 16 and the square root of 3. Well, as before, we know that the square root of 16 is 4. Do we know what the square root of 3 is? We really don't. So, because we don't know what the square root of 3 is, and it's an irrational number, we just want to write it next to it. And there goes our simplified form. 4 times the square root of 3. Same thing here with 75. Take the largest perfect square that can go into 75 evenly. All right, so we have 25 times 3. Make sure you take the square root of both of them. All right, and the square root of 25 is 5. We don't know the square root of 3, so we're going to leave that. But we need to do the same thing here with 27. We want to take the largest perfect square that goes into 27. Let's try 9 times 3. So take the square root of 9, square root of 3. The square root of 9 is 3. The square root of 3, well, we don't really know. So we just want to leave it and put it next to each other. Now that we have simplified the both radical expressions, we want to go ahead and bring down this plus sign so that we can perform our indicated operation. Okay? Because we have like terms, such as the square root of 3, we know that our answers are going to have the square root of 3. Well, with that being said, we just need to perform the operation between the coefficients. So 5 plus 3 gives you 8. And your answer is 8 times the square root of 3. Okay. Well, that was then. This is now. All right. The only difference with now is back then, you were told that you could not take the square root of a negative number. And that's true if we're looking at the set of real numbers. Okay, hence the real number system. But now we're in the complex number system. In order to take the square root of a negative number, we had to go through a different number system to work this out, or simply be able to simplify this expression. And now we can. Okay? The only difference is you just have this negative in front of here. So you can go back and start by taking the negative out. So we know that 16 times negative 1 gives you negative 16. Well, let's take the square root of both of them. All right, we know the square root of 16, again, is 4. What's the square root of negative 1? Well, by definition, that's I. So our answer is 4I. Yeah, I know it's a little tricky, but something that you got to work with and practice on. Okay, because that's going to come up in quadratic equations pretty soon. All right, again, the square root of negative 48. Well, let's break it down. Let's take out that negative 1 first. So we know 48 times negative 1 gives us negative 48. All right, we need to take the square root of 48 and the square root of negative 1. Well, we got to go back and break down 48 first into a perfect square and another number. So that's 16 and 3. Now take the square root of 16 and the square root of 3. The square root of 16 is 4. Okay. We have the square root of 3 there that we don't know. And now the square root of negative 1 again is I. So we got to bring this all together. All right. This will be written and seen as 4I times the square root of 3. Okay. Notice that I brought the I in between the 4 and the square root of 3 here. Okay. That's there because that's how you're going to see it usually. You want to definitely make sure that the I is next to the coefficient if possible, and not the radical, not behind the radical. All right. Here we go again. The square root of 75. We said the square root of 75 gave us the square root of 25 times the square root of 3. So that was 5 times the square root of 3. And if we break down this negative 27, that gives us 27 times negative 1. Well, let's take the square root of 27. The square root of 27 times the square root of negative 1. Well, we got to break that 27 down again, just as we did before, into a perfect square of such. So that's 9 times 3. Let's take the square root of 9 and the square root of 3. So 3 times the square root of 3. And don't forget, you have this negative 1 here, so that's an I. So let's rewrite all of this into an expression that we can see. So you have 5 times the square root of 3 plus 3I times the square root of 3. All right. Notice that 5 times the square root of 3 does not have the same terms as 3I times the square root of 3, so we can't combine them. That's our final answer. Okay. One thing to remember out of a lot of things, but this is one thing that's really important. When we're talking about radicals, and that's what we're going to be talking about throughout the duration of from now to for winter break, when you have A So when we're taking the square root of A and we're multiplying it times the square root of B, it's just so much easier and simpler for us to multiply them first and then talk about the square root of it. You can do that so that you have less problems later on in the end. That's just one way of thinking of it. It's not always the best way, but it's one way of thinking of it so you don't have too many problems. It definitely um, solves a lot of problems and simplifies them much quicker as opposed to trying to figure out the square root of the first number and multiply it times the square root of the second number. And you'll see that in an example coming up. So make sure you write that down. All right, also, when you're dividing here, when I have the square root of A divided by the square root of B, let's try to make sure we put that as a fraction with the square root sign on the outside. Okay? Because sometimes, again, it's much easier to reduce the fraction first and then take the square root of it as opposed to trying to do it individually. And again, this is just sometimes, but it's just something good for you to remember in practice. All right. So today, we practiced the even problems only. So the even problems that we were looking at were 12, 14, 18, 20, 24, and 26. Okay? And we practiced those in partners. That way we can get used to seeing the negative under the square root sign. So number 12. You have 4 times the square root of negative 7. All right? Not much you can do here other than bring out that negative. All right? So you have 4 times the square root of 7 times the square root of negative 1. Well, what's the square root of negative 1? By definition, it's I. So as we're rewriting this, you're going to have 4I times the square root of 7 as your answer. Number 14 here for you. A lot of us probably struggle with this, but again, you can do this one of two ways, and you'll still get the right answer. So you have the square root of negative 50 and square it. Now, some of us saw it as this. Some of us said, well, okay, if I take the square root of negative 50 and I multiply it times the square root of negative 50, I'm going to get a big number. And that's right. And that's fine. However, remember your square root property. If I am squaring something that's being square rooted, my answer is just what's under the square root to begin with. Why are we doing so much work? Don't do more work than you need to. So the answer was negative 50. All right, number 18. So you have 4x times the square root of negative x. Again, let's rewrite it as 4x times the square root of x times the square root of negative 1. We know that by definition, the square root of negative 1 is just I. So we're going to rewrite it as 4xi times the square root of x. And you're done. Number 20. Number 20 says the square root of negative 2 times the square root of 8. All right. Again, if you looked at the remember that we talked about before you did this, it says when I have the square root of A times the square root of B, just rewrite it as a times b. So you have the square root of negative 2, which is your a, times the 8. Well, we know that the square root of we know that negative 2 times 8 is negative 16. So you're looking at the square root of negative 16. Now let's break that down. Okay, so you have the square root of 16 times the square root of negative 1. Remember, the square root of negative 1 is what? It's I. What's the square root of 16? 4. So the answer is 4i. Okay, so that's number 20. Moving on. Question 24. You have the square root of negative 24 over the square root of 3. Again, if we use the definition that we talked about, the square root of a divided by the square root of b, let's go ahead and bring it under one umbrella. So that's going to be the square root of negative 24 over 3. Okay? We know that 3 goes into 24 how many times? That's 8 times. And a negative divided by a positive is negative. So we're really simplifying the square root of negative 8. So let's do that. So we have the square root of 8 times the square root of negative 1. We know that the square root of negative 1 is just I, so cross it out. But we have to do some work with the square root of 8. What two numbers can I multiply together to get 8? And one of them has to be a perfect square. So we want to break it down to 4 and 2. Well, the square root of 4 is 2, and the square root of 2, well, we don't really know. So we just want to bring it down. Let's just remember to rewrite it. 2i times the square root of 2. That's how you're going to see it written on the test if it's multiple choice. And that's the expectation. All right. Number 26, you have 11 times the square root of negative 6 over 11 times the square root of 2. All right. The first thing I would do as a math student, if I see 11 in my numerator and 11 in my denominator, I probably would cancel those out because 11 divided by 11 is 1. So I would start by rewriting that first. So what I'm really looking at is the square root of negative 6 over the square root of 2. Again, by the principles and the properties that we got before we started this, we said that we will take this and write it as a fraction, a single fraction under the square root. So that's the square root of negative 6 divided by 2. Well, can 2 go in as negative 6 evenly? It sure can. That gives us the square root of negative 3. Okay? So let's break it out. You have the square root of 3 times the square root of negative 1. What's the value of negative 1, the square root of negative 1? That's I. All right? We can't do nothing with the square root of 3, so we just write it as I times the square root of 3. And there goes the answer. Again, there are many practice problems on this. I do urge you to continue to practice with these problems and definitely work it out. It's only going to take practice and it takes time. The last thing that we spoke about today was the quadratic formula. Sometimes you have to go to an old friend to meet new friends. Okay, so the topic was quadratic formula and the discriminant, and we'll continue this. Within this quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac over 2a, we have two hidden treasures that are there. One of them you know as the axis of symmetry. The axis of symmetry is x equals negative b over 2a, or the opposite of b over 2a. The other is called the discriminant. The discriminant is b squared minus 4ac. That's all of this stuff. Sorry. That's all of this under the radical sign. That's your discriminant. Okay? And you've seen this before, and you're pretty familiar with this, but you just never knew what it was called and the importance of it. So today you're going to look at the importance of it. In fact, the discriminant helps describe the nature of the roots. Okay? Your roots are your answers when you solve a quadratic. Basically, how many times does this parabola or this quadratic crosses the x-axis? Now, the discriminant helps you set limits as to how many times the parabola crosses the x-axis, or what does that mean? So there are three cases of this. The first case is when your discriminant b squared minus 4ac is less than 0. Okay? Well, first think about what type of numbers are less than 0. All right? Those numbers that are less than 0 are negative numbers. So we just talked about negative numbers, and because your discriminant is located under a square root symbol, it's important to note that if the discriminant is negative, then the square root of a negative number is an imaginary number. So when we have this case right here, when b squared minus 4ac is less than 0, our roots are two imaginary or complex roots. Two imaginary or complex roots. What that means is it doesn't touch the x-axis at all. So it may look like this. Okay? Or it may look like this. Okay? It's anything that does not touch the x-axis. Does not cross the x-axis. Did not touch it. It may get close to it, but it will not touch it. Okay? Our second case, case number 2, is when b squared minus 4ac is equal to 0. Well, if b squared minus 4ac, or our discriminant, equals 0, well, what's the square root of 0? That's 0. And it's only one 0 that we know about. So if your discriminant equals 0, the nature of your roots is that you're going to have one real solution. Okay? In other classes, this is also called a repeated root. Okay? And what this looks like is you have your parabola, it touches and it goes back up at that one point. Okay? Have my parabola, it touches and go back down at one point. It only touches once. And that's your root. That's your solution. Well, we dealt with the negative and we dealt with when the discriminant equals 0. So the only other thing left is when b squared minus 4ac is greater than 0, or when it's positive. Okay? When b squared minus 4ac is positive, that means the number under the square root is positive. So that allows us to have two real solutions. And what that looks like is it goes down and comes back up. 1, 2. Goes up, comes back down. 1, 2. Okay. Well, of course, we have some examples here. I brought a couple of old friends back out from our former quiz here to help us out with the discriminant. So we have f of x equals 4x squared plus 1. Well, just like you did the quadratic equation, or excuse me, the quadratic formula rather, list out what your a is, what your b is, and what your c is. Nothing changes. This is still part of the quadratic formula. So in this case, a is 4. B looks like it's 0, and C is 1. So using the discriminant, B squared minus 4AC, we're going to plug in. So B is 0, so 0 squared minus 4 times 4 times 1. Well, we know 4 times negative 4 is negative 16. Negative 16 times 1 is still negative 16. So our discriminant is negative 16, or it's negative, because it's less than 0. So if we go back, if our discriminant is less than 0, that means we have case 1 going on here. That means you have two imaginary complex roots. Okay. Next problem, we have f of x equals 4x squared minus 1. Again, a equals, b equals, c equals. All right, a equals 4, b equals 0, and c looks like it's negative 1. So let's plug it into our discriminant. B squared minus 4 times a times c, or 4ac. So again, b is 0 squared minus 4 times 4 times negative 1. All right. So we have negative 4 times positive 4. That's negative 16. But that's being multiplied times negative 1. So that's actually positive 16. So in this case, 16 is greater than 0. So if we look back at our cases or our rules here, we have a case 3. When b squared minus 4ac is greater than 0, you have two real solutions. So that's how you describe that. Okay. Down here in the bottom left, you have f of x equals 2x squared minus 32. So a equals, b equals, c equals. A equals 2, b equals 0, and c equals negative 32. So we want to use our discriminant here. So you get b squared minus 4 times a times c. Again, b is 0, so we have 0 squared minus 4 times 2 times negative 32. Okay, so we have negative 4 times 2 is negative 8. Negative 8 times 30, negative 32 is 256. So that's a positive 256. So that means that 256 is greater than 0. And we will have, if we go back to our chart here, we should have two real solutions. Okay. And last but not least,